Chapter 7 Helicopter Instrument Procedures Introduction. This chapter presents information on IFR helicopter operations in the National Airspace System. Advances in avionics technology installed in helicopters such as Global Positioning System, GPS, and Wide Area Augmentation System, WAAS, are bringing approach procedures to heliports around the country. The ability to operate helicopters under IFR increases their utility and safety. Helicopter IFR operators have an excellent safety record due to the investment in IFR-equipped helicopters, development of instrument approach procedures, IAPs, and IFR-trained flight crews. The safety record of IFR operations in the Gulf of Mexico is equivalent to the safety record of the best-rated airlines. Manufacturers are working to increase IFR all-weather capabilities of helicopters by providing slower minimum instrument airspeeds, VMINI, faster cruising speeds, and better autopilots and flight management systems, FMS. As a result, in October 2005, the first civil helicopter in the United States was certified for flight into known icing conditions. Figure 7.1. Helicopter Instrument Flight Rule, IFR, certification. It is very important that pilots be familiar with the IFR requirements for their particular helicopter. Within the same make, model, and series of helicopter, variations in the installed avionics may change the required equipment or level of augmentation for a particular operation. The Automatic Flight Control System / Autopilot / Flight Director, AFCS/AP/FD, equipment installed in IFR helicopters can be very complex. For some helicopters, the AFCS/AP/FD complexity requires formal training in order for the pilots to obtain and maintain a high level of knowledge of system operation, limitations, failure indications, and reversionary modes. For a helicopter to be certified to conduct operations in instrument meteorological conditions, IMC, it must meet the design and installation requirements of Title 14 Code of Federal Regulations, 14 CFR, Part 27, Appendix B, Normal Category, and Part 29, Appendix B, Transport Category, which is in addition to the Visual Flight Rule (VFR) requirements. These requirements are broken down into the following categories: flight and navigation equipment, miscellaneous requirements, stability, helicopter flight manual limitations, operation specifications, and minimum equipment list (MEL). Flight and navigation equipment. The basic installed flight and navigation equipment for helicopter IFR operations is listed under 14 CFR Part 29, Section 29.1303, with amendments and additions in Appendix B of 14 CFR Parts 27 and 29 under which they are certified. The list includes clock, airspeed indicator, sensitive altimeter. A sensitive altimeter relates to the instrument's displayed change in altitude over its range. For copter category, CAT2 operations, the scale must be in 20-foot intervals. Adjustable for barometric pressure. Magnetic direction indicator, free air temperature indicator, rate of climb, vertical speed indicator, magnetic gyroscopic direction indicator, standby bank and pitch, attitude indicator, non-tumbling gyroscopic bank and pitch, attitude indicator, speed warning device, if required by 14 CFR Part 29, miscellaneous requirements, overvoltage disconnect, instrument power source indicator, adequate ice protection of IFR systems, alternate static source, single pilot configuration, thunderstorm lights, transport category helicopters, stabilization and automatic flight control system, AFCS. Helicopter manufacturers normally use a combination of a stabilization and/or AFCS in order to meet the IFR stability requirements of 14 CFR Parts 27 and 29. These systems include aerodynamic surfaces, which impart some stability or control capability that generally is not found in the basic VFR configuration. Trim systems provide a cyclic centering effect. These systems typically involve a magnetic brake/spring device and may be controlled by a four-way switch on the cyclic. This system requires hands-on flying of the helicopter. Stability Augmentation Systems, SAS, provide short-term rate damping control inputs to increase helicopter stability. Like trim systems, SAS requires hands-on flying. Attitude Retention Systems, ATT, return the helicopter to a selected attitude after a disturbance. Changes in attitude can be accomplished usually through a four-way beep switch or by actuating a force trim switch on the cyclic, which sets the desired attitude manually. Attitude retention may be a SAS function or may be the basic hands-off autopilot function. Autopilot systems, APs, provide for hands-off flight along specified lateral and vertical paths. The functional modes may include heading, altitude, vertical speed, navigation tracking, and approach. APs typically have a control panel for mode selection and indication of mode status. APs may or may not be installed with an associated FD. APs typically control the helicopter about the roll and pitch axes, cyclic control, but may also include yaw axis, pedal control, and collective control servos. Flight directors, FDs, provide visual guidance to the pilot to fly selected lateral and vertical modes of operation. The visual guidance is typically provided by a single cue, commonly known as a V-bar, which provides the indicated attitude to fly and is superimposed on the attitude indicator. Other FDs may use a two-cue presentation known as a cross-pointer system. These two presentations only provide attitude information. A third system, known as a three-cue system, provides information to position the collective as well as attitude, roll and pitch cues. The collective control cue system identifies and cues the pilot what collective control inputs to use when path errors are produced or when airspeed errors exceed preset values. The 3-cue system pitch command provides the required cues to control airspeed when flying an approach with vertical guidance at speeds slower than the best rate of climb, VROC speed. The pilot manipulates the helicopter's controls to satisfy these commands, yielding the desired flight path, or may couple the autopilot to the FD to fly along the desired flight path. Typically, FD mode control and indication are shared with the autopilot. Pilots must be aware of the mode of operation of the augmentation systems and the control logic and functions in use. For example, on an instrument landing system, ILS, approach and using the 3-cue mode, lateral, vertical, and collective cues, the FD collective cue responds to glide slope deviation, while the horizontal bar cue of the cross pointer responds to airspeed deviations. However, the same system when operated in the 2-cue mode on an ILS, the FD horizontal bar cue responds to glide slope deviations. The need to be aware of the FD mode of operation is particularly significant when operating using two pilots. Pilots should have an established set of procedures and responsibilities for the control of FD/AP modes for the various phases of flight. Not only does a full understanding of the system modes provide for a higher degree of accuracy and control of the helicopter, it is the basis for crew identification of a faulty system. Helicopter Flight Manual Limitations. Helicopters are certificated for IFR operations with either one or two pilots. Certain equipment is required to be installed and functional for two-pilot operations, and additional equipment is required for single-pilot operation. In addition, the Helicopter Flight Manual, HFM, defines systems and functions that are required to be in operation or engaged for IFR flight in either the single or two-pilot configurations. Often, in a two-pilot operation, this level of augmentation is less than the full capability of the installed systems. Likewise, a single-pilot operation may require a higher level of augmentation. The HFM also identifies other specific limitations associated with IFR flight. Typically, these limitations include, but are not limited to, minimum equipment required for IFR flight, in some cases, for both single-pilot and two-pilot operations, VMINI, minimum speed, IFR, Figure 7.2, NI, never exceed speed, IFR, maximum approach angle, weight and center of gravity, CG limits, helicopter configuration limitations, such as door positions and external loads, helicopter system limitations, generators, inverters, etc., system testing requirements. Many avionics and AFCS, AP, and FD systems incorporate a self-test feature, pilot action requirements. For example, the pilot must have hands and feet on the controls during certain operations, such as an instrument approach below certain altitudes. Final approach angle/descent gradient for public approach procedures can be as high as 7.5 degrees/795 feet/nm. At 70 knots indicated airspeed, KIAS, no wind, this equates to a descent rate of 925 fpm. With a 10-knot tailwind, the descent rate increases to 1056 fpm. Copter point-in-space pins. Approach procedures are restricted to helicopters with a maximum VMINI of 70 kias and an IFR approach angle that enables them to meet the final approach angle/descent gradient. Pilots of helicopters with a VMINI of 70 kias may have inadequate control margins to fly an approach that is designed with the maximum allowable angle/descent gradient or minimum allowable deceleration distance from the missed approach point, MAP, to the heliport. The copter pin's final approach segment is limited to 70 kias since turn containment and the deceleration distance from the map to the heliport may not be adequate at faster speeds. For some helicopters, engaging the autopilot may increase the VMINI to a speed greater than 70 kias, or in the go-around, GA, mode, require a speed faster than 70 kias. Figure 7.2, it may be possible for these helicopters to be flown manually on the approach or on the missed approach in a mode other than the GA mode. Since slower IFR approach speeds enable the helicopter to fly steeper approaches and reduces the distance from the heliport that is required to decelerate the helicopter, you may want to operate your helicopter at speeds slower than its established V-mini. The provision to apply for a determination of equivalent safety for instrument flight below V-mini and the minimum helicopter requirements are specified in Advisory Circulars, AC 27-1, Certification of Normal Category Rotorcraft, and AC 29-2, Certification of Transport Category Rotorcraft. Application guidance is available from the Rotorcraft Directorate Standards Staff, ASW 110, 2601 Meacham Boulevard, Fort Worth, Texas, 761374298, 817-222-5111. Performance data may not be available in the HFM for speeds other than the best rate of climb speed. To meet missed approach climb gradients, pilots may use observed performance for similar weight, altitude, temperature, and speed conditions to determine equivalent performance. When missed approaches utilizing a climbing turn are flown with an autopilot, set the heading bug on the missed approach heading, and then at the map, engage the indicated airspeed mode, followed immediately by applying climb power and selecting the heading mode. This is important since the autopilot roll rate and maximum bank angle in the heading select mode are significantly more robust than in the nav mode. Figure 7.3 represents the bank angle and roll limits of the S-76 used by the FAA for flight testing. It has a roll rate in the heading select mode of 5 degrees per second with only 1 degree per second in the nav mode. The bank angle in the heading select mode is 20 degrees, with only 17 degrees in the nav changeover mode. Furthermore, if the airspeed hold mode is not selected on some autopilots when commencing the missed approach, the helicopter accelerates in level flight until the best rate of climb is attained, and only then will a climb begin. WAAS Localizer Performance, LP, lateral-only pins testing conducted in 2005 by the FAA at the William J. Hughes Technical Center in New Jersey for helicopter pins also captured the flight tracks for turning missed approaches. Figure 7.4, the large flight tracks that resulted during the turning missed approach were attributed in part to operating the autopilot in the nav mode and exceeding the 70 km limit. Operation specifications: a flight operated under 14 CFR Part 135 has minimums and procedures more restrictive than a flight operated under 14 CFR Part 91. These Part 135 requirements are detailed in their operation specifications, OP specs. Helicopter Air Ambulance, HAA, operators have even more restrictive OP specs. Shown in Figure 7.5 is an excerpt from an OP specs detailing the minimums for precision approaches. The inlay in Figure 7.5 shows the minimums for the ILS Runway 3R approach at Detroit Metro Airport. With all lighting operative, the minimums for helicopter Part 91 operations are a 200-foot ceiling, and 1,200 feet runway visual range, RVR, 1/2 airplane category of visibility but no less than 1/4 SM/1,200 RVR. However, as shown in the OP specs, the minimum visibility this Part 135 operator must adhere to is 1,600 RVR. Pilots operating under 14 CFR Part 91 are encouraged to develop their own personal OP specs based on their own equipment, training, and experience. Minimum Equipment List (MEL), a helicopter operating under 14 CFR Part 135 with certain installed equipment inoperative is prohibited from taking off unless the operation is authorized in the approved MEL. The MEL provides for some equipment to be inoperative if certain conditions are met. Figure 7.6, in many cases, a helicopter configured for single-pilot IFR may depart IFR with certain equipment inoperative provided a crew of 2 pilots is used. Under 14 CFR Part 91, a pilot may defer certain items without an MEL if those items are not required by the Type Certificate, CFRs, or Airworthiness Directives, ADs, and the flight can be performed safely without them. If the item is disabled, removed, or marked inoperative, a logbook entry is made. Pilot proficiency helicopters of the same make and model may have variations in installed avionics that change the required equipment or the level of augmentation for a particular operation. The complexity of modern AFCS, AP, and FD systems requires a high degree of understanding to safely and efficiently control the helicopter and IFR operations. Formal training in the use of these systems is highly recommended for all pilots. During flight operations, you must be aware of the mode of operation of the augmentation system and the control logic and functions employed. Figure 7.2, Helicopter VFR minimums. Helicopters have the same VFR minimums as airplanes with 2 exceptions. In Class G airspace or under a Special Visual Flight Rule, SVFR, clearance, Helicopters have no minimum visibility requirement but must remain clear of clouds and operate at a speed that is slow enough to give the pilot an adequate opportunity to see other aircraft or an obstruction in time to avoid a collision. Helicopters are also authorized, 14 CFR Part 91, Appendix D, Section 3, to obtain SVFR clearances at airports with the designation No SVFR on the sectional chart or in the chart supplement CS. Figure 7.7 shows the visibility and cloud clearance requirements for VFR and SVFR. However, lower minimums associated with Class G airspace and SVFR do not take the place of the VFR minimum requirements of either Part 135 regulations or respective op specs. Knowledge of all VFR minimums is required in order to determine if a PINS approach can be conducted or if a SVFR clearance is required to continue past the MAP. These approaches and procedures are discussed in detail later. Helicopter IFR takeoff minimums. 14 CFR Part 91 imposes no takeoff minimums on the helicopter pilot. However, rotorcraft flight manuals may require the helicopter to attain at least VMINI before entering IMC. For most helicopters, this requires a distance of approximately half mile and an altitude of 100 feet. If departing with a steeper climb gradient, some helicopters may require additional altitude to accelerate to VMINI. To maximize safety, always consider using the Part 135 operator standard takeoff visibility minimum of half statute mile, SM, or the charted departure minima, whichever is higher. A charted departure that provides protection from obstacles has either a higher visibility requirement, climb gradient, and/or departure path. Part 135 operators are required to adhere to the takeoff minimums prescribed in the Instrument Approach Procedures, IAPs, for the airport. Helicopter IFR alternates. The pilot must file for an alternate if weather reports and forecasts at the proposed destination do not meet certain minimums. These minimums differ for Part 91 and Part 135 operators. Part 91 operators. Part 91 operators are not required to file an alternate if, at the estimated time of arrival, ETA, and for 1 hour after, the ceiling is at least 1,000 feet above the airport elevation or 400 feet above the lowest applicable approach minima, whichever is higher, and the visibility is at least 2 sm. If an alternate is required, an airport can be used if the ceiling is at least 200 feet above the minimum for the approach to be flown and visibility is at least 1 sm, but never less than the minimum required for the approach to be flown. If no instrument approach procedure has been published for the alternate airport, the ceiling and visibility minima are those allowing descent from the MEA, approach, and landing under basic VFR. Part 135 operators. Part 135 operators are not required to file an alternate if, for at least 1 hour before and 1 hour after the ETA, the ceiling is at least 1,500 feet above the lowest circling approach minimum descent altitude, MDA. If a circling instrument approach is not authorized for the airport, the ceiling must be at least 1,500 feet above the lowest published minimum or 2,000 feet above the airport elevation, whichever is higher. For the IAP to be used at the destination airport, the forecasted visibility for that airport must be at least 3 sm or 2 sm more than the lowest applicable visibility minimums, whichever is greater. Alternate landing minimums for flights conducted under 14 CFR Part 135 are described in the op specs for that operation. All helicopters operated under IFR must carry enough fuel to fly to the intended destination, fly from that airport to the filed alternate if required, and continue for 30 minutes at normal cruising speed. Helicopter instrument approaches. Many new helicopter IAPs have been developed to take advantage of advances in both avionics and helicopter technology. Standard instrument approach procedures to an airport. Helicopters flying standard instrument approach procedures, SIAP, must adhere to the MDA, or decision altitude for Category A airplanes, and may apply the 14 CFR Part 97.3, D1, rule to reduce the airplane category of visibility by half but in no case less than 1/4 sm or 1,200 RVR. Figure 7.8, the approach can be initiated at any speed up to the highest approach category authorized. However, the speed on the final approach segment must be reduced to the Category A speed of less than 90 km before the map in order to apply the visibility reduction. A constant airspeed is recommended on the final approach segment to comply with the stabilized approach concept, since a decelerating approach may make early detection of wind shear on the approach path more difficult. Figure 7.9, when visibility minimums must be increased for inoperative components or visual aids, use the inoperative components and visual aids table, provided in the front cover of the U.S. Terminal Procedures, to derive the Category A minima before applying any visibility reduction. The published visibility may be increased above the standard visibility minima due to penetrations of the 20:1 and 34:1 final approach obstacle identification surfaces, OIS. The minimum visibility required for 34:1 penetrations is 3/4 sm and for 20:1 penetrations 1 sm, which is discussed in Chapter 5 of this handbook. When there are penetrations of the final approach OIS, a visibility credit for approach lighting systems is not allowed for either airplane or helicopter procedures that would result in values less than the appropriate 3/4 sm or 1 sm visibility requirement. The 14 CFR Part 97.3 visibility reduction rule does not apply, and you must take precautions to avoid any obstacles in the visual segment. Procedures with penetrations of the final approach OIS are annotated at the next amendment with visibility reduction by helicopters NA. Until all the affected SIAPs have been annotated, an understanding of how the standard visibilities are established is the best aid in determining if penetrations of the final approach OIS exists. Some of the variables in determining visibilities are decision altitude, DA/M.D.A, height above touchdown, HAT, height above airport, HAA, distance of the facility to the map, or the runway threshold for non-precision approaches, and approach lighting configurations. The standard visibility requirement, without any credit for lights, is 1 sm for non-precision approaches and 3/4 sm for precision approaches. This is based on a category at airplane 250 to 320 feet HAT/HA, for non-precision approaches a distance of 10,000 feet or less from the facility to the map, or runway threshold. For precision approaches, credit for any approach light configuration. For non-precision approaches, with a 250 HAT, configured with a medium-intensity approach lighting system, MALSR, Simplified Short Approach Lighting System (SOR), or approach lighting system with sequenced flashing lights, ALSF-1 normally results in a published visibility of half sm. Consequently, if an ILS is configured with approach lights or a non-precision approach is configured with MALSR SOR, or ALSF-1 lighting configurations and the procedure has a published visibility of 3/4 sm or greater, a penetration of the final approach OIS may exist. Also, pilots are unable to determine whether there are penetrations of the final approach OIS if a non-precision procedure does not have approach lights or is configured with ODLs, MALs, or SOL/SALS lighting since the minimum published visibility is 3/4 sm or greater. As a rule of thumb, approaches with published visibilities of 3/4 sm or more should be regarded as having final approach OIS penetrations, and care must be taken to avoid any obstacles in the visual segment. Approaches with published visibilities of half sm or less are free of OIS penetrations, and the visibility reduction in Part 97.3 is authorized. Copter-only approaches to an airport or heliport pilots flying copter SIAPs, other than GPS, may use the published minima with no reductions in visibility allowed. The maximum airspeed is 90 km on any segment of the approach or missed approach. Figure 710 illustrates the Copter ILS or LOC RWY-13 approach at New York/LaGuardia, LGA Airport. Copter ILS approaches to category, CAT, facilities with DAs no lower than a 200-foot HAT provide an advantage over a conventional ILS of shorter final segments and lower minimums, based on the 20:1 missed approach surface. There are also copter approaches with minimums as low as 100-foot HAT and 1/4 sm visibility. Approaches with a HAT below 200 feet are annotated with the note, Special Aircrew and Aircraft Certification required since the FAA must approve the helicopter and its avionics, and the flight crew must have the required experience training and checking. The ground facilities, approach lighting, signal in space, hold lines, maintenance, etc. and air traffic infrastructure for Cat-2 ILS approaches are required to support these procedures. The helicopter must be equipped with an AP, FD or head-up guidance system, alternate static source, or heated static source, and radio altimeter. The pilot must have at least a private pilot helicopter certificate, an instrument helicopter rating, and a type rating if the helicopter requires a type rating. Pilot experience requires the following flight times: 250 pilot in command, PIC 100 helicopter pick, 50 night pick, 75 hours of actual or simulated instrument flight time, including at least 25 hours of actual or simulated instrument flight time in a helicopter or a helicopter flight simulator, and the appropriate recent experience training and check. For Copter Cat-2 ILS operations below 200 feet HAT, approach deviations are limited to 1/4 scale of the localizer or glide slope needle. Deviations beyond that require an immediate missed approach unless the pilot has at least one of the visual references in sight and otherwise meets the requirements of 14 CFR Part 91.175C. The reward for this effort is the ability to fly Copter ILS approaches with minima that are sometimes below the airplane Cat-2 minima. The procedure to apply for this certification is available from your local Flight Standards District Office, FSDO. Copter GPS approaches to an airport or heliport. Pilots flying Copter GPS or WAAS SIAPs must limit the speed to 90 km on the initial and intermediate segment of the approach and to no more than 70 km on the final and missed approach segments. If annotated, holding may also be limited to 90 km to contain the helicopter within the small airspace provided for helicopter holding patterns. During testing for helicopter holding, the optimum airspeed and leg length combination was determined to be 90 km with a 3 nautical miles outbound leg length. Consideration was given to the wind drift on the dead reckoning entry leg at slower speeds, the turn radius at faster airspeeds, and the ability of the helicopter in strong wind conditions to intercept the inbound course prior to the holding fix. The published minimums are to be used with no visibility reductions allowed. Figure 711 is an example of a Copter GPS pins approach that allows the helicopter to fly VFR from the map to the heliport. The final and missed approach protected airspace providing obstacle and terrain avoidance is based on 70 km, with a maximum 10 knot tailwind component. It is absolutely essential that pilots adhere to the 70 km limitation and procedures that include an immediate climbing and turning missed approach. Exceeding the airspeed restriction increases the turning radius significantly and can cause the helicopter to leave the missed approach protected airspace. This may result in controlled flight into terrain, CFIT, or obstacles. If a helicopter has a VMINI greater than 70 knots, then it is not capable of conducting this type of approach. Similarly, if the autopilot in go-around mode climbs at a VIA greater than 70 knots, then that mode cannot be used. It is the responsibility of the pilot to determine compliance with missed approach climb gradient requirements when operating at speeds other than VY or VIA. Missed approaches that specify an immediate climbing turn have no provision for a straight-ahead climbing segment before turning. A straight segment results in exceeding the protected airspace limits. Protected obstacle clearance areas and surfaces for the missed approach are established on the assumption that the missed approach is initiated at the DA point and for non-precision approaches no lower than the MDA at the map, normally at the threshold of the approach end of the runway. The pilot must begin the missed approach at those points. Flying beyond either point before beginning the missed approach results in flying below the protected obstacle clearance surface, OCS, and can result in a collision with an obstacle. The missed approach segment U.S. Standard for Terminal Instrument Procedures, TIRPS, criteria for all copter approaches take advantage of the helicopter's climb capabilities at slow airspeeds, resulting in high climb gradients. Figure 712, the OCS used to evaluate the missed approach is a 20-to-1 inclined plane. This surface is twice as steep for the helicopter as the OCS used to evaluate the airplane missed approach segment. The helicopter climb gradient is, therefore, required to be double that of the airplane's required missed approach climb gradient. A minimum climb gradient of at least 400 feet/nm is required unless a higher gradient is published on the approach chart. For example, a helicopter with a ground speed of 70 knots is required to climb at a rate of 467 fpm. 467 fpm equals 70 km times 400 feet per nautical mile/60 seconds. The advantage of using the 20-to-1 OCS for the helicopter missed approach segment instead of the 40-to-1 OCS used for the airplane is that obstacles that penetrate the 40-to-1 missed approach segment may not have to be considered. The result is the DA/M.D.A may be lower for helicopters than for other aircraft. The minimum required climb gradient of 400 feet/nm for the helicopter in a missed approach provides 96 feet of required obstacle clearance, ROC, for each nm of flight path. Helicopter approaches to VFR heliports. Helicopter approaches to VFR heliports are normally developed either as public procedures to a pins that may serve more than one heliport, or as a special procedure to a specific VFR heliport that requires pilot training due to its unique characteristics. These approaches can be developed using very high-frequency omnidirectional range, VOR, or automatic direction finder, ADF, but area navigation, RNAV, using GPS is the most common system used today. RNAV using the WAAS offers the most advantages because it can provide lower approach minimums, narrower route widths to support a network of approaches, and may allow the heliport to be used as an alternate. A majority of the special procedures to a specific VFR heliport are developed in support of HA operators and have a proceed visually segment between the map and the heliport. Public procedures are developed as a PINS approach with a proceed VFR segment between the map and the landing area. These PINS proceed VFR procedures specify a course and distance from the map to the available heliports in the area. Approach to a PINS. The note associated with these procedures is, proceed VFR from, named map, or conduct the specified missed approach. They may be developed as a special or public procedure where the map is located more than 2 sm from the landing site, the turn from the final approach to the visual segment is greater than 30 degrees, or the VFR segment from the map to the landing site has obstructions that require pilot actions to avoid them. Figure 7.13 is an example of a public pins approach that allows the pilot to fly to one of 4 heliports after reaching the map. For Part 135 operations, pilots may not begin the instrument approach unless the latest weather report indicates that the weather conditions are at or above the authorized IFR or VFR minimums as required by the class of airspace, operating rule and/or op specs, whichever is higher. Visual contact with the landing site is not required. However, prior to the map, for either Part 91 or 135 operators, the pilot must determine if the flight visibility meets the basic VFR minimums required by the class of airspace, operating rule and/or op specs, whichever is higher. The visibility is limited to no lower than that published in the procedure until canceling IFR. If VFR minimums do not exist, then the published map must be executed. The pilot must contact Air Traffic Control, ATC, upon reaching the map, or as soon as practical after that, and advise whether executing the missed approach or canceling IFR and proceeding VFR. To proceed VFR in uncontrolled airspace, Part 135 operators must observe minimum regulatory VFR conditions, but under some conditions, such as provided for in 14 CFR 135.613 for HA operators, specific weather minimums are required when near the map and the heliport of intended landing. These minimums apply regardless of whether the approach is located on the plains of Oklahoma or in the Colorado mountains. However, for heliports located farther than 3 nautical miles from the heliport, Part 135 HA operators are held to an even higher standard, and the minimums and lighting conditions contained in Figure 7.15 apply to the entire route. Mountainous terrain at night with low light conditions requires a ceiling of 1,000 feet and either 3 sm or 5 sm visibility depending on whether it has been determined as part of the operator's local flying area.
In Class B, C, D, and E surface area airspace, ISVFR clearance may be obtained if SVFR minimums exist.
On your flight plan, give ATC a heads up about your intentions by entering the following in the remarks section: request SVFR clearance after the map. Approach to a specific VFR heliport. The note associated with these procedures is, proceed visually from named map, or conduct the specified missed approach. Due to their unique characteristics, these approaches require training. They are developed for hospitals, oil rigs, private heliports, etc. As specials, they require flight standards approval by a letter of authorization, LOA, for Part 91 operators or by op specs for Part 135 operators. For public procedures, the heliport associated with these procedures must be located within 2 sm of the map, the visual segment between the map and the heliport evaluated for obstacle hazards, and the heliport must meet the appropriate VFR heliport recommendations of AC 155392, heliport design. The pin's optimum location is 0.65 nautical miles from the heliport. This provides an adequate distance to decelerate and land from an approach speed of 70 km. Certain airframes may be certified to fly at reduced Vmini or below Vmini speeds as a result of flight control design or adherence to AC 292, certification of transport category rotorcraft. In these cases, an approach procedure stating the minimum certified airspeed or flight below Vmini should be annotated on the approach procedure. The distance also permits optimal blending of obstacle clearance criteria with non-instrument heliport approach areas. The visibility minimum is based on the distance from the map to the heliport, among other factors, for example, height above the heliport elevation when at the map MDA. The pilot is required to acquire and maintain visual contact with the heliport final approach and takeoff, FATO, area at or prior to the map. Obstacle or terrain avoidance from the map to the heliport is the responsibility of the pilot. Pilots need to level off when reaching the MDA, which may occur before arriving at the map, until reaching the visual approach angle on the approach path to clear the obstacles. If the required weather minimums do not exist, then the published map must be executed at the map because IFR obstruction clearance areas are not applied to the visual segment of the approach, and a missed approach segment protection is not provided between the map and the heliport. As soon as practicable after reaching the map, the pilot advises ATC whether canceling IFR and proceeding visually or executing the missed approach. Inadvertent IMC. Whether it is a corporate or HA operation, helicopter pilots sometimes operate in challenging weather conditions. An encounter with weather that does not permit continued flight under VFR might occur when conditions do not allow for the visual determination of a usable horizon, for example, fog, snow showers, or night operations over unlit surfaces such as water. Flight in conditions of limited visual contrast should be avoided since this can result in a loss of horizontal or surface reference, and obstacles such as wires become perceptually invisible. To prevent spatial disorientation, loss of control, LOC, or fit, pilots should slow the helicopter to a speed that provides a controlled deceleration in the distance equal to the forward visibility. The pilot should look for terrain that provides sufficient contrast to either continue the flight or to make a precautionary landing. If spatial disorientation occurs and a climb into IMC is not feasible due to fuel state, icing conditions, equipment, etc., make every effort to land the helicopter with a slight forward descent to prevent any sideward or rearward motion. All helicopter pilots should receive training on avoidance and recovery from inadvertent IMC with emphasis on avoidance. An unplanned transition from VMC to IMC flight is an emergency that involves a different set of pilot actions. It requires the use of different navigation and operational procedures, interaction with ATC and crew member resource management, CRM. Consideration should be given to the local flying area's terrain, airspace, air traffic facilities, weather, including seasonal effects such as icing and thunderstorms, and available airfield/heliport approaches. Training should emphasize the identification of circumstances conducive to inadvertent IMC and a strategy to abandon continued VFR flight in deteriorating conditions. This strategy should include a minimum altitude/airspeed combination that provides for an off-airport/heliport landing, diverting to better conditions, or initiating an emergency transition to IFR. Pilots should be able to readily identify the minimum initial altitude and course in order to avoid fit. Current IFR on route and approach charts for the route of flight are essential. A GPS navigation receiver with a moving map provides exceptional situational awareness for terrain and obstacle avoidance. Training for an emergency transition to IFR should include full and partial panel instrument flight, unusual attitude recovery, ATC communications, and instrument approaches. If an ILS is available and the helicopter is equipped, an ILS approach should be made. Otherwise, if the helicopter is equipped with an IFR approach-capable GPS receiver with a current database, a GPS approach should be made. If neither, an ILS or GPS procedure is available, use another instrument approach. Upon entering inadvertent IMC, priority must be given to control of the helicopter. Keep it simple and take one action at a time. Control. First, use the wings on the attitude indicator to level the helicopter. Maintain heading and increase to climb power. Establish climb airspeed at the best angle of climb but no slower than V-min. Climb. Climb straight ahead until your crosscheck is established. Then make a turn only to avoid terrain or objects. If an altitude has not been previously established with ATC to climb to for inadvertent IMC, then you should climb to an altitude that is at least 1,000 feet above the highest known object and that allows for contacting ATC. Communicate. Attempt to contact ATC as soon as the helicopter is stabilized in the climb and headed away from danger. If the appropriate frequency is not known, you should attempt to contact ATC on either very high frequency VHF 121.5 or ultra high frequency UHF 243.0. Initial information provided to ATC should be your approximate location, that inadvertent IMC has been encountered, and an emergency climb has been made, your altitude, amount of flight time remaining, fuel state, and number of persons on board. You should then request a vector to either VFR weather conditions or to the nearest suitable airport/heliport that conditions will support a successful approach. If unable to contact ATC and a transponder code has not been previously established with ATC for inadvertent IMC, change the transponder code to 7700. A radio altimeter is a necessity for alerting the pilot when inadvertently going below the minimum altitude. Barometric altimeters are subject to inaccuracies that become important in helicopter IFR operations, especially in cold temperatures. IFR Heliport's AC 155392, Heliport Design, provides recommendations for heliport design to support non-precision, approach with vertical guidance, APV and precision approaches to a heliport. When a heliport does not meet the criteria of AC 155392, FAA Order 8260.42, United States Standard for Helicopter Area Navigation, RNAV requires that an instrument approach be published as a special procedure with annotations that special aircrew qualifications are required to fly the procedure. Currently, there are no operational civil IFR heliports in the U.S., although the U.S. military has some non-precision and precision approach procedures to IFR heliports.